here we are going to analyze a cantilever beam that is subject to 10 Newton force. This is subject to 10 Newton force, and here this end is fixed. To achieve the fixity, what we do, we basically use screw to tighten it, and thereafter we placed some iron block to have proper fixity there. So today we are going to model this beam using 3D solid element. Here you can see the dimension is given as a 10 mm is your depth, and this is your width. That width is basically your 50 mm. Okay. That is given there, and the property is given your 30 GPa and Poisson ratio is 0.3. And here what we'll try to do, we'll try to find the maximum deflections. What is the maximum deflection is coming due to this 10 Newton force. And thereafter we'll try to see that how we can do the convergence study. In the convergence study, we can do by two ways. One is that by increasing the element, okay, or you can see the finer element, that is called H convergence. Other way we have to get the convergence is by increasing the polynomial. Okay, in that way we can also achieve the convergence. One is your H convergence, another is your P convergence. In the H convergence, we increase the number of elements, and P convergence we increase the polynomial. Polynomial in the sense we increase that your order of the element. Here in that P convergence, basically the polynomial, we use higher polynomial in the sense we increase the order of the polynomial. Here for your cell element, we can use S4R, which is your linear element, and thereafter we also can use your quadratic element, that is your S8R. Now if you come to our 3D solid beam, in that case we can use 8-noded brick element. Thereafter also we can use 20-noded brick element. Okay, that is C3D8R. One is the C3D8R, another is C3D20R. R is for your reduced integration. So here we can achieve convergence by two ways. One is by increasing the number of element. Okay, another is by increasing the order of the polynomial. Order of the polynomial means we will increase the order of the element. Here we can use linear element, and thereafter we can use your quadratic element. In that way we can achieve the convergence. That we will see here. Another is we'll try to plot the load deflection graph. Okay, we'll see how we can get load deflection graph by in ABAQUS. In ABAQUS, by default we used to get force. Okay, force with respect to time, and displacement also with respect to time, but we need the displacement force versus displacement. We'll see how we can achieve that, and at the end we'll try to get the solution from the analytical solution. Okay, so analytical solution we know that is your PLQ by 3EI. That we know PLQ by 3EI. If we get it, you will observe that for this case, our deflection is coming 2.66 e to the power -2. That value will come, that is in meter. If you do all the things in meter, it will come at 2.66 to the power -2, or you can say it will come 26.66 mm. That amount displacement will come at the end, and we'll try to see how much value we are getting in ABAQUS, and how we can achieve the convergence, and what is the converged value, and whether that converged value is close to this value or not. That also we'll see. Now we'll go to the ABAQUS and we'll try to model it using 3D solid element. Here you can see it has already one model. So what we can do, we can go for new model from here, or from here also we can add one model. Okay, without exiting from here, we can add one more model here. Okay, you can see it is model 2. Now here you can see this part is now blank. Now again we know that to model a beam or any structures, to model infinite element, we know that to model, here we'll see how we can model the beam in ABAQUS. Okay, so to model a beam, we have to go through various module. Here you can see we have part module, we have property module, we have assembly module, we have step module, we have load module, we have mesh module, and then we have job module. This module will be required to model the beam here. Okay, so what we are going to do first here, we are going to create the part. So here you can see the part, we can make the geometry. So here we can make the geometry by two way. One is your, you can make the geometry by two way. One is your, we can make the geometry of the beam by the two way. We can take this side view of the beam and then we can extrude it in this way. You can have a 3D beam. Other way is that you make the cross section first and then we extrude it in this directions and we can make the beam. Because in ABAQUS we can make the beam or 3D geometry here in two ways. Okay, so what we are going to do here, we will try to paper in this way. So here we can see our beam look like this. Okay, so what we are going to do, we will give the first coordinate at 0 and 0, and this coordinate will give 50 e to the power minus 3, comma 10 e to the power minus 3. Okay, because 10 mm is our depth, and this is your 50, and this is your 10. So this will be our 50 to the minus 3, 10 to the minus 3. That will give, and then we'll extrude it up to 1 meter. Okay, so now we'll go to the ABAQUS and we'll see how we can do it. Now here we'll click on the part and then we'll choose 3D deformable solid, and here the extrusion process will follow. Now here we'll put as a value 5 because our maximum dimension is 1 meter. Our beam having a length of 1 meter, so we're putting maximum size as a 5. Now we'll choose this one, rectangle one. Now here you can see it is asking pick in the starting corner. So what we'll do, we'll put 0, 0, and opposite corner will give your 50 e to the power minus 3, 10 e to the power minus 3. One thing you should keep in your mind that ABAQUS do not have any inherent unit system. ABAQUS do not have any inherent unit system. What you have to do, you have to be consistent with the unit. What I used to follow, Newton meter unit. So here you can see all the dimensions in meter, all the dimensions I am giving in meter, and load I will try to give in Newton. Okay, so here you can do Newton meter unit, or you also can follow Newton mm. Nothing is that what are the result you will get, that you have to interpret. So since I am giving in all Newton and meter, I'll also get the result in meter and stress also in Newton meter square. If you give Newton mm, in that case deflection you will get in mm, stress also will get Newton mm. Okay, so in that way you also have to interpret. So you should be very consistent with the unit in case of your mass, in case of your dimension, in case of our elasticity or other property. In that case, you always have to be consistent with the unit system. So here, what we did, we first give that one corner 0, 0, and then we give opposite corner 50 to the minus 3, 20 to the minus 3, and we have created this part. Okay, now we'll click on the done, and then here you can see it is asking what is the depth. So our depth is 1 meter. I'll give 1 meter. Okay, now here you can see we have created the geometry of the beam. We have created the geometry of the beam in the part module. Now what we will do, we have to go for property module. Here in the property module, what we used to do, we used to first create the material library, and then we used to create section library, and then we used to assign that section. So assign section means you will see once we create material library, and in the section library you automatically incorporate the material. Okay, we'll choose, there will be options, we can choose what type of material material 1, material 2, material 3, what material you want to incorporate in the section, that we can choose there. And in the assign section we assign section can do that. You can create material. Okay, so I can write aluminum ALU. Okay, now since we are doing elastic analysis, static analysis, since we are doing static analysis, we will give only elastic property here. Elastic property is 30 GPa, 30E9, 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 and our percentage is 0.3. Okay, that is the property of aluminum, and we'll click on OK. Now here you can see, if you click it here, you can see we have created one material in the material library. Here you can create a lot of material and you can make it as a material library. Now here, what we can do, we can create the section. Now here you can see it is asking section, so you can write 3D solid. You can write solid 3D. You can write solid 3D, and here you can see it is solid, and we are considering it as a homogeneous. Now here you can see it is taking material library. It is taking material from the material library as a aluminum that we have created earlier. From here we can choose other. If you have lot of material, you can choose other material also. Now click it here. Now here we will assign the section here. Okay, now we can assign the section here. You can see we are assigning 3D solid 3D that we have created. And here you can see we are assigning aluminum property here, and that also solid and homogeneous. Now we'll click it here. Here you can see the color has changed. That means we have defined the property correctly. Now we'll go to the next module, that is your assembly module. In the assembly module, what we are going to do, we are going to create an instance. What we are going to do, we are going to create an instance. Here, if we click here, you can create the instance. So what ABAQUS is to do, ABAQUS is to create an instance, and thereafter ABAQUS is to work on the instances and give the result. Okay, so here you can see we can create the instance by two ways. One is the dependent, another is independent. Okay, dependent instance, if you choose, then you do mesh on the part. Okay, if you use independent instance, and then you can use mesh. You can do the meshing on instance. Okay, so here we can see that what is the things is coming while doing the meshing. So basically, dependent and independent terms, dependent and independent instance will be helpful doing the meshing. Okay, if you do, we'll see while doing the meshing. We'll see while doing the meshing. Okay, so we have completed your assembly module. Now what we are going to do, we will create steps, and in the steps we will try to define what type of analysis we are going to do. So here you just click here, and then here you can see it is selecting static general. Here you can choose the different type of analysis, but here we'll choose static general since we want to do static analysis. Now here, what are the value, default value is coming. We're going to choose here. If you see, you can go to the increment and you can adjust it here. You can adjust some parameter, but here we'll choose the default value and we'll click it OK. So we have completed 4 module, part module, property module, assembly module, and step module. Now we can go for meshing. Now see that meshing part actually meshing part was mentioned in the assembly while doing the instances. Okay, now we'll see how it is affecting. So what we're going to do, we'll click on the seed. So in the meshing, okay, now here you can see it is saying that we cannot do the meshing in the assembly, but it is saying that you can select the part to do the meshing. So here, if you choose, we can do the meshing. Okay, now here while doing the meshing, you have to keep one thing in mind. In the meshings, we used to do in 2 steps. We used to do in 2 steps. First step is that we used to create the seed value. In the seed value, what we are going to do, we are going to define the nodal values. Here, we basically you can say we used to create the nodes. In the seed, we basically create the nodes, and then what we used to do, we used to go for meshing. Basically, in the meshing, what we are going to do, we are going to join the node and create the mesh. So here you can see we have created one meshing. Okay, on meshing we have created the meshing in the beam. We have created the meshing in the beam. Here at the bottom you can see we have created 20 elements for our beam. We have created 20 elements for our beam. So here what we can do, we will note down this number of element and we will try to increase the element and we'll see up to which element we can give our converge result. Okay, so here we have initially used 20 elements, then we try to use more number of element. Okay, we'll try to use more number of element and we'll see how we can achieve the convergence. So what we are going to do, we are going to note down in a copy that what is the number of element. So here it is 20 and the right column will write what is the deflection is coming. So okay, what is the deflection is coming. That will write after the analysis. So here we have created 20 element in the beam. Okay, and we'll do the analysis. So to the analysis, what we have to do, we have to apply the loading and the boundary condition and all. We can do the analysis. Okay, so here we'll go to the loading part, and then what we're going to do in the loading, we'll see how we can apply the loading. Here what we're going to do, we'll apply the load as a concentrated force. Okay, we'll apply the load as a concentrated force. So what we'll do, we'll click on concentrated force here and we can select this node and this node and we'll divide the total load the two number of elements. Okay, since we've chosen two elements, we will try to divide the total load to two elements. So here I'll choose 5 and here I'll put the load as a RAM. Here we'll try to give the load as a RAM. Their amplitude is as a RAM. Here try to give the amplitude as a ramp. The ramp is basically linearly increasing load. So initially at 0 point load will be 0. At maximum point at 1 point our load will be 5 and that load increment will be linear in nature. So here you can see that load is acting in upward direction. So what we can do, we can give minus sign here so that it will act in downward direction. Here you can see load is applied in the downward direction. Now what we are going to do, we are going to select the boundary conditions. Here we are going to select the boundary conditions. So here we'll create the boundary and you can see we can apply the boundary condition by two ways. One is your encaster option, one is your encaster option, another is your displacement option. Encaster is basically one type of boundary condition where all the displacement is 0. Encaster is one type of boundary condition where all the displacement is 0. If you have U1, U2, U3, all displacement will be 0. If you use displacement type boundary conditions, in that case, you can choose what type of options, what type of displacement you want to make 0. If you use displacement boundary condition, then you have options to choose what type of displacement you want to make 0. What type of displacement you want to make 0. So here in the encaster, if you click continue and you just select this region and click OK, and then here you can select this encaster. Here you can see U1, U2, U3, UR1, UR2, UR3 all are 0. So U1 is here displacement along X direction, UR2 is the displacement along Y direction, U3 is the displacement along Z direction, and UR basically rotation about X axis, rotation about Y axis, and U3 is rotation about Z axis. So all we are making 0. Those are in the beginning stage. In that case, you should choose this encaster options to define fixed boundary conditions. Okay, if you are in advanced stage, in that case you can choose from this option. Here you can choose the area and here you can see you have the options. You can make the individual component as a 0. Here if you select it and you can give it 0. Like that you can provide your boundary conditions. Since I have provided already once, since I have provided the boundary conditions, since I have provided the boundary conditions, I am not going to provide it here one more time. Okay, so I will cancel it. Okay, now here you can see we have already applied our loading. We have already applied the loading and the boundary conditions. We have already applied the loading and the boundary conditions. Here, one more thing you can do, you can check the module, what are the module you have done. Okay, and you can run the program. So here you can see here in the part module, we have make the geometry. In the property module, we have defined the material property. In the assembly, we have create the instance, and then in the steps, we have create what type of analysis we want to perform. Here we have selected our static analysis, and in the loading we have defined the loading and the boundary conditions. In the meshing we have done the meshing. Okay, now we can submit the job and we can see what are the deflection is coming. Since we can see what are the deflection is coming. Here you can see it is already showing some analysis. So what we can do, you can delete it. Okay, you can delete it and you can create a new one. So here you can write beam 3D 10 Newton force. Okay, otherwise you can write can beam 3D 10 Newton force. Okay, since it is model 2, I have selected model 2 here. Now I'll continue and I'll make it okay, and then I'll submit the job and we'll wait to get the solution done. Here you can see it is showing status as running. Okay, if you want to see what type of error is coming or warning is coming, and then you can click on the monitor options. From here you can see whether there is error or there is a warning. Okay, since we don't have any error, any warning, so it is empty here, it is blank here. But if there is some error, in that case, you can check it from here. Now you can see the job has completed. Now what we can do, we can go to the result and we can see what is the maximum deflection is coming. Here U is there and maximum is your U2. Here you can see our maximum deflection is coming as your 2.45. 2.45 E0, that means 2.45 meter it is coming. Okay, now you can see this deflection amount is too high. Okay, we have 1 meter beam and we have 2.45 meter displacement. Okay, that is too high. Now what we're going to do, we are going to increase the number of elements and we can see how we can get the converged result. Now what we're going to do, we'll go to the meshing, and we'll try to increase the number of elements. So here I can select here. Okay, now it is saying again that you cannot work on assembly. You have to select part. Now I've selected part. Now I will click on the shade value here. Now here you can see initially it was 0.5. Now I select as a 0.01 and I'll apply it here. Here it is giving a warning that if we do this job, if you do this, your old mesh will be deleted. So let us agree with that, and you can see we have created that seed value, that is your nodal value, and now here you can see we have now final element. Okay, now once we create a new meshing, okay, once we create a new meshing, in that case we need to check, we should check whether loading condition and boundary condition is working fine or not. Here you can see it is working fine. Now we can again submit the job and again we have to wait for the solution. So here what we got displacement of 2.45 mm with the 20 element. Now here you can see how many elements we have created. Initially we have created 20 element. Now we have to see we have created 500 element. Okay, so now we have created 500 element, and now we'll see what is the maximum deflection is coming. So now go to your displacement U and you'll go to U2. Now here you can see still it is your 2.45 meter. Okay, now again what we're going to do, we'll increase the meshing to larger extent and we'll see what is the deflection is coming. So now what we're going to do, we'll go to our here, we'll go to this value again, and then we'll try to make one more 0 here, and we'll see. Okay, we'll see what are the deflection is coming. So now here you can see we have created 50,000 element. We have created 50,000 element. Okay, we have created 50,000 element. Now what we're going to do, we're going to submit the job again and we'll see what is the deflection is coming. It may take a little more time because number of elements is more, so correspondingly number of degree freedom also will be large. So our K matrix also will be large. So ABAQUS may take long time. Let us see. this is 500,000 element, it will take more time. Yes, this much amount element may not be required. We'll see how much minimum element we should require to get the converged result. How much minimum number of element will be required to get the converged result. Okay, so let us see what the result is coming with 500,000 element. So now you can imagine 500,000 elements. That means there will be degree of freedom, large number of degree of freedom, and there will be K matrix with larger size. And obviously, ABAQUS will take a long time to get the inverse of it and to get the solution. Taking too long time, since ABAQUS is taking too long time, what we can do, we can change the number of element. We can reduce the number of element little bit. Okay, here 500,000 is too much. We can reduce it lower amount, and we can see what is the minimum number of element is required to get the converged results. What I can do, I can kill the job and you can resubmit it. Okay, since I am not able to operate on the computer, it is almost hanged. What I can do, I will try to kill the job. Either I will try to kill the job or I will close ABAQUS. Okay, if I kill the job, that's fine. ABAQUS probably will not create a log file. If I close the job forcefully, we close the job forcefully. If you close the ABAQUS forcefully, in that case, ABAQUS will create a log file for this problem, and I will not be able to submit the same file name. But what I am going to do, I am going to change the file name and resubmit it. Okay, so what I'll do, I will change the meshing with lesser amount of element. Okay, I'll change the meshing with lesser amount of element, and again I'll try to submit it. Since I have used very large number of element, I had to abruptly close. Here you can see the program is still running. What I can do, I can kill the program. I can kill the running process. So I have done it. It will take some time to stop it. So in between, what I am going to do, I am going to remesh it. Okay, now I'll try to reduce the mesh size. Okay, I'll try to reduce the mesh size, and here I'll use seed by edge, and here I'll use seed by edge here, and I'll select the edge here 1, 2, 3, and 4. Okay, here you can choose 4 edge by pressing Shift button. Okay, I've selected 4 edge. Now I'll try to make the number of element as 100 element. Okay, I'll make the element as 100 element along the length. Now here I'll make, this is your 5 number of element, and here also 5 number of element. Along the depth, I'll make 4 number of element. Okay. On the depth, I'll take 4 number of element, and here again I'll go to loading. I will see how the load is working or not. Yes, loading is working. Boundary condition is also working. Boundary also working. Boundary condition is also working. Now I'll create another model here that you can write cant beam. Okay, cant beam 3D, and then write TRI trial 2. Now I will submit here. I'll submit here. It is saying that the following part are not meshed. So it is saying that not meshed. Okay, why it is saying so? Why it is saying so? Okay, why it is saying so? Okay, yes, I have not created the mesh. Yes. Okay. Here we have 100 element like this. We have created element. Now here we have created. Here we have created 20,000. So 2,000. Here we have created 2,000 element. Here we have created 2,000 element. Now go to the loading. It is working. Yes, it is working. Now I'll submit the job. Now what I can do, I'll go to job. I'll create the job, and I'll write cant beam 3D, and then trial. Okay, trial 2. And I want to submit. Yes, so we have created 2000 element, and I will see what are the result is coming. What are the displacement coming? What is the maximum displacement? That we'll see. It's completed. Now we'll see U2 here. Maximum deflection is coming 2.83 is 2.83 to the power -2 now. Okay, is 2.83 to the -2. Now you can see it is coming little close. Okay, it is coming little close. We had initial displacement, that is what we had displacement as per analytical model is 26 mm, 26.66 mm. Here we are getting 2.83. So it is close. Now one more trial we'll do. We'll increase the meshing. So now we'll do one thing. We'll increase the mesh size along this width. Now here my number it is. I will try to make it as 20. No, sorry, 10. I'll make it as 10. This side also I'll use as a 10. Here also I'll use 10. So number I will make it 10. Okay, now if we make it 10, we'll see. We'll do the meshing and we'll see. Here you can see we have created element of 10,000. We'll see we have created a element of 10,000. Okay, now we'll see what is the result is coming. The result is coming. We'll submit the job one more time and we'll see what is the result is coming. It is completed. Now we'll see our maximum deflection U2. Now you can see the maximum deflection is coming as your 2.68 e to the power -2. This is our deflection. Okay, now what happened till now we have used linear element. Now we will do one more thing. We'll use higher order element. What we are going to do, we will use higher order element and see what are the deflection. Okay, what are the deflection? So here we'll choose mesh. We'll go to the mesh. Here you can see in the mesh options we're going mesh here top, and then we're choosing element type. It is saying select the region, so I'll select the region. I click on done, and then I'll use quadratic element and I'll make it. Okay, so now we have created the model with higher order element, and then we'll see loading, whether loading is working fine. Yes, loading is working fine here. Now I will run the job and we'll see what are the deflections, what is the maximum deflection is coming. Now job is completed. We'll see the maximum deflection. Here you can see maximum deflection with 10,000 element and your quadratic element value is coming 2.656. So now you can see it is very close. Okay, here you can see by choosing appropriate element type and appropriate element number, we can converge our model. So this is the way we should do the analysis. This is the way we should do the analysis in ABAQUS. Now we'll try to plot. Now we'll try to plot load versus deflections. Now we'll try to plot load versus deflection. So to do that, what we have to do, we have to select the node for which we need the deflection, and we have to select the nodes for which we need the forces. ABAQUS directly cannot give the force on the loading point. ABAQUS cannot give the force from the loading point. We have to take it as a reaction force, and we have to take the sum of all the reaction force acting on the node, so that you can get the total force, or you can say total reaction force, and you can plot load versus deflection. So one end will calculate, one end will request ABAQUS to calculate all the reaction forces acting in that y direction and all the displacement, okay, average of all the displacement acting in the free end or loading point, and we'll plot it. So we'll calculate average displacement that is occurring at the end and your total reaction force acting the support. Total reaction acting in y direction in the support. Okay, and we plot it. So to do that, what we have to do, we have to go to the assembly, and then what we have to do, we have to select node and you have to create a node set for which we need the deflection and for which we need the reaction. So now I'll go to tool and then I'll go to create and I'm going to create a node set of displacement. So displacement nodes. Okay. Now here this is our free end. Okay, where load is acting there. Now what I'm going to do, I'm going to select the nodes. So here I have to see how we can do that. Since this model here you can see that if you plot in the YZ plane, if you plot YZ plane, I can see the nodes here. Here you can see if you plot in YZ plane, I can see the nodes. So now from this option, we can plot in the YZ plane here like this. Okay. If you observe that this option is not here in your ABAQUS model, then you can go to the view and then you can go to the toolbar, and from here you can go to the view options. From that you can get it. Okay. So I will try to use this option and we will try to select the node so that we can select all the edge node to make a set. Here you can see, we'll see what are the node we have selected. Yes, we have selected half of the node. This is our fixed end. Okay, this is our fixed end. So what we are going to do, now we'll try to select for reaction force. We'll try to select. Now we'll try to make a node set for reaction force RF2. Create a node set for the reaction force. Like that, we can select the node and we can define the node set for the reaction force. Here you can see we have created node set. This is combination of 341 nodes. Okay, in the same way, we have to do the node set the right side. Do the node set on the right side. So here again, we'll try. Here we can do. You can use your shift button, mouse button, and you can use this one to rotate view option. Select that node set for you. Okay. Yeah, again we'll try to create node set. So tool set, go to create here. Then we will create displacement node. This node. Now here, select this node. Okay. And now here you can see we have selected the node here and we make it done. Here you can see we have selected 341 node for the displacement. So now what we'll do, we'll take the average of all the displacement occurring here and summation of all the reaction forces occurring in the support. Now what we will do to get that, you have to go to the step and then you have to define history output. History output we have to make, this is your displacement output. At the displacement here you have to choose set and then here you have to select displacement node and here you have to select your U2. Okay. Next again we have to create your RF2 reaction force. Okay. Next again what you do, you have to go to the next what you do, you have to go to your history output, then your right reaction, continue here, set, here you select RF2 and then here you just select RF2 here. Okay. Now we have selected. Now what we'll do, we'll submit the job again and we'll try to plot it. We'll submit the job and we'll try to plot it. job is completed. We go to the result. Now to plot it, what you have to do, you have to go to here, you create XY data, go to here and then to select ODB history output because we have requested in the history output of the steps. Okay, so we'll go to the history output option and then click continue. Now here you can see we have RF2. So what we'll do, we'll press the shift button and then I'll go down. I'll try to go down. I'll try to go down. Okay, I'll select all the nodes. I'll select all the node here. Here and save is the sum. So here we can write reaction force. You can save it reaction force. Here you can see the total load is 10 and with time it is what? So at one time it is total load is there and it is increasing linearly. That actually your load that we have selected while submitting the job in the steps. Okay, that you have selected in the steps as a RAM type load. So it is also showing as a RAM. Now what we'll do is save the displacement. We'll save the average displacement and see how the displacement is coming. We'll save the average displacement. Here I'll save it as average your displacement. Now I'll save. Now here you can see displacement also is coming with respect to time. Only thing is that displacement it is in opposite order. It is minus 20 like that. It should be at 0 time. There is 0 displacement like that. We'll see how can deal with this. How we can deal with this. Now again you have to click it here. Then again you have to create on XY data, or here you have to click on operate on XY data. Go to that. Now here you have to choose combine. Since displacement is coming in negative order, so what I'll do, I'll put minus sign here. Then I use mouse to select displacement. Then I'll double click on the reaction force. Then I'll plot. Now here you can see we have plotted the load versus displacement. Okay, since we have chosen our dimension unit in a meter, so our displacement also is coming in a meter. So it is basically nearly 26 point something mm. So here at the end this value is 26 point something. Okay, 26 mm. But here we are getting in meters, so it is 1025 and then it will be 0.06, 026 like that. That will be there. Okay, so this is the way we can plot load versus deflection. Okay, and this is the way we can plot load versus deflection graph or force versus displacement graph. Now we can print it. We can save this as a print button. So here you can click on print and then you can choose grayscale and then you can choose file option here and here TI file and you can write some name is FFFF and okay. Here you can see that file has been created at C drive and temp folder. So what you have to do, you have to go to C drive and the temp folder. You go to the C drive and then go to your temp folder, temporary folder, and find the FF file and open it. Here you can see we have plotted force versus displacement and we have also saved the file. Now you can copy paste this file and paste it in your Word file to make a document. So this is the way you should plot force versus displacement graph. So what we have done, we have modeled a 3D cantilever beam and we have seen that maximum deflection that is occurring at the end and maximum deflections is coming nearly 26.66 mm. And then what we did the convergence study. We try to do convergence study using linear element and then we have chosen quadratic element and we have seen that quadratic element is giving good result in comparison to the linear element. Okay, in that sense with that limited number of element. Okay, though if you use the more number of element, in that case, or linear element can also give good result. So what we have done, we have basically model a cantilever beam using 3D solid element And then we have analyzed with 20 element, 500 element, and 2000 element, and we obtained the displacement and noted it down. And then we increase the element to 10,000, and we have observed the deflection is coming close to our exact solution. And then what we did, we use higher order element, that is our quadrilateral element, and we have seen that also giving good result. And we also done the convergence study. Okay, we'll plot it. We'll see how the data is changing with the number of elements. So we'll see. And here you can write this is your deflection. Now we write node number as 20. Then we have 500. Then we have 2000, and then we have 10,000 element, and we have noted down the deflection, that is was 2.45, then 2.45, and then we have 2.83 e to the power minus 2, and then we have 2.656 power minus 2. Okay. This is the deflection we got according to our node number. Now what we'll do, we'll plot it. We'll plot it. Here you can see that convergence result is coming like this. Okay, so here you can see after 1000 element we are getting, after 10,000 element we are getting little bit converged result. Okay, that is basically you can say that our result, is close to our approximate solution. Our result is close to our exact solution. Our result is close to our exact solution. So this is the way we can analyze. If you don't have that exact solution, then what you can do, we have to do more trial using 20,000 element, and then 50,000 element, and you have to see whether your result is changing or not. Okay, if you see that your result is not changing after 20,000 or 50,000 element, then you can stop some between there and you can carry on your analysis in ABAQUS. Okay, so this is the way basically you have to do the convergence study, and you have to decide how many number of element you should choose and what type of element you should choose. Okay, so we have learned that both the way we can do the convergence by increasing the number of element and by using higher order polynomial, or other way you can say in higher order element. Both the way we can get our converged result. Okay, so here you have some role as an engineer, you have some role to choose your number of element and type of element so that you can get converged result. So I hope you get some idea. How to model beam in ABAQUS, how to do convergence study, how to do load versus deflection plot, and how to plot that convergence data and decide how many number element you should choose and what element you should choose. I hope you get some idea. Thank you.